When you ring a bell, the bell begins to vibrate when impacted. This creates sound waves. The Doppler effect is a change in the frequency of sound as the source and observer move toward or away from each other. If I rang the bell seen in the video while the boat was traveling towards the dock at 5 meters per second, the frequency heard by someone standing on the dock can be calculated using the formula frequency detected equals frequency of source times speed of sound plus speed of observer over speed of sound minus speed of source. Here I am just plugging in the known values given to find the frequency heard by the observer on the dock. Using the Doppler effect equation, the frequency heard by the observer is about 450 Hz. Tension force is the force caused by a rope or string on an object. Me pulling the line created tension force on both me and the boat. If you look at the force diagram, the tension force is greater than the friction force, causing the boat to move towards the force I am applying. Pulleys change the direction of the tension force, but not the amount of force applied. Say I pulled on the rope with 100 newtons of force. In an ideal world, throughout the whole pulley system, the tension force on the line pulling up the sail would be 100 newtons, no matter what. The torque applied to the winch handle in this picture can be calculated. Torque is the rotational equivalent of force. The equation for torque is Fr sine theta. Since the handle is applying force in the clockwise direction, torque is negative. After plugging in all the necessary information, the torque is calculated to be equal to about negative 13 Newton meters. Angular velocity can be calculated using the equation W equals change in theta over period. Theta is 1 revolution, or 2 pi. Plugging in the period, 9.93 seconds, the angular velocity is calculated to about 6.75 radians per second. The answer is positive because the disk is moving counterclockwise. Rotational velocity can be converted to linear velocity through the equation V equals RW. The linear velocity of the disk unrolling the head sail is about 1 meter per second. In free fall, the only force affecting the buoy is gravity, and it falls straight down. To calculate the final velocity after free fall, the equation v final squared equals v initial squared plus 2ad is used. The initial velocity is 0, and the acceleration due to gravity is 9.8 meters per second squared. The velocity when the buoy hits the ground is about 5 meters per second. If I threw a float directly horizontal at 5 meters per second, how far would the float go? That problem is solved using projectile motion. First, the y direction of the problem needs to be solved to find the time. After time is found, it can be plugged into the x direction equation to find the distance the float went. I calculated that the float landed about 2.14 meters away. In the magical ideal world, all energy in a system is conserved. A great way to show this conversion is through bar charts, signifying different points in the motion of an object. In this case, a float being tossed in the air. At point 1, the float is moving and above the baseline, so the gravitational and kinetic energies are not at their maximums and are both visible on the chart. At point 2, the float is at its maximum height and therefore has no kinetic energy and all gravitational energy. At point 3, the float is at the base level, the water, and therefore is only using kinetic energy, with no gravitational potential energy. In solving a conservation of energy problem, the first step is setting everything equal because energy is conserved. EA equals EV equals EC. In this problem, we are finding final velocity with the other variables assigned in the diagram. After plugging in the equations, I decided I didn't need to include the middle equation, because energy is conserved through the whole motion. At impact with the water, the final velocity was about 9.3 meters per second.